All right, so we've got some more T-shirt announcements before we get started.
Okay, so you guys, so you guys are probably all sick of us by now, but
Thank you so much for contributing.
thank you
to
so
t-shirt
much for
design.
contributing to the T-shirt fund.
We're just trying to make you all roughly happy.
And democracy is inefficient. So we have one more poll for you. We have a winning design. We just need to decide where it goes, front or back, and what sort of arrangement we have. So we have 3 different options for like the arrangement of the designs. If you could vote on that by ideally like 8 p.m. today,
By 8 p.m. today.
that would be by 8 p.m. today, period. That would be incredible. And once we have that, we'll be all finalized and set to go, and we won't need to send you any more polls. So
We'll send you a form asking you for money instead. Yes. It's okay. It's not. So the plan is probably Thursday or Friday. We'll just send out, maybe also on Slack, so that everyone kind of sees it. Like, just the website or the providers that we're using will allow you to just pay yourselves, and they'll all get shipped here out on one day, and then we'll distribute them. So that removes the shuffling of the money around. Hopefully.
So some of us were thinking that maybe it'd be nice to have a taxi mug. And so maybe we could use some of those old designs to.
we will create, we were planning to create stickers of a lot of the other designs that you can then put on mugs, whatever else you want.
So, like, having a tumbler or a mug is an option, and then
Let me sort of postpone further discussion about this because we're eating into the lecture time, but thank you both very much. And so let's head back to Simon for his next lecture.
And one of the messages is that they're very constrained. You start writing 2 to 2 amplitudes, 2 to n amplitude, taking soft limits, various things. They're extremely constrained. It's not true that you can write any Lagrangian and it's going to make sense. But the constraints we use so far had very little to do with causality, in case you were wondering the connection with the title of my lectures. So we mostly use unitarity. Unitarity is what told us that null states that were longitudinal modes in a massless case had to decouple. So Q mu amplitude equals 0. And we use crossing symmetry, so we can use Feynman diagrams and all channels has to work out. But we haven't used causality in any deep way yet. Okay? On the other hand, I hinted at the end of last lecture that using causality, we could get stronger constraints in some cases, like massive gravity. So we'll get to that. And the other sort of a message is that amplitudes involving spinning particles grow with energy. It's a very basic fact. And ultimately, it's just because with more Lorentz indices, you get more derivatives. But what this tells us is that whenever you have effective theories involving spinning particles, at least anything that goes beyond Yang-Mills, will be some kind of EFT, low energy effective theory, that needs to be UV completed somehow. So that's how we should think about the theories involving. They're never fundamental theories. The things we have to UV complete in some fashion. So the general way to think about this in this Wilson language is you imagine that there exists some microscopic theory and that describes somehow physics at all scales. But then you integrate out all of the short distance fluctuations and you end up with this low energy or long distance effective theory, which, for example, will look like some kind of gradient expansion, like this. And the idea is that, and as far as the predictions much below the cutoff go, you can assume that this low energy theory is equivalent to a local theory where you only have local, like polynomial and derivative interactions here. Okay, so these two things will be equivalent to each other at energies much below the cutoff. And this framework is this standard Wilsonian framework there's actually 2 different kind of situations here. So sometimes we do know the UV. So it's useful to distinguish the situation. So sometimes this happens, and there's And it's still a very useful tool. I'm just going to give you a few examples. So you know, if I want to describe the gas, the dynamics of air in this room, you know, you sort of know it's made of molecules, but you're not going to use that description to to describe what happens to air. You will use more macroscopic concepts like density and velocity and pressure and basically hydrodynamics, right? So this is an example of an effective theories where even though we have a macroscopic picture, it's much more useful to zoom out and use the effective theory to understand what happens. There's a lot of situations, you could keep going on, but another very familiar situation is full QED. If you think of it as a theory of electrons, positrons, protons, photons, if you integrate out the positron, you end up with non-reducible QED, also known as atomic physics. So if you want to understand atomic physics, integrating out the positron is a very good idea. Then you just have some non-reducible Hamiltonian acting on a bunch of electrons, and a lot of condensed matter can take that as a starting point, right? So yeah, maybe one more example. If you take QCD at very low energies, the part of the force between protons can be understood in terms of exchange on pions and so on. So there's a lot of cases where we know the UV theory, but we pretend all the details of this UV theory end up, as far as the long wavelength physics goes, end up packaged in some of these coefficients in some effective theory. And there are situations where we just don't know what the UV theory is. And maybe one more I could add in is this, where we think we know is string theory, but instead of in string theory, we use the low energy effective theories a lot. And sometimes we don't. Sometimes we don't know. Sometimes we don't know the UV. Okay? And the sort of thing I will be talking about today are more focused on this situation. Okay? And in this situation, you think of this expansion here essentially as a way of parameterizing your ignorance about the short distance physics that you don't know about. Different UV physics will give you different values of these coefficients, which you can try to go and measure. And one thing which is one we can ask there is, okay, on this effective theory picture, I can write down a bunch of, it's Lagrangians, not very constrained. I can write down a bunch of different Lagrangians, and it looks like the values of the constant are arbitrary. But the question one can ask is, what effective theories do arise from UV theories that are causal? So that is the main question. It's a well-defined question we can try to ask. So which EFTs admit causal UV completion? Okay. And notably, there will be sign constraints, but also constraints on the magnitude of these coefficients, as we will see. Okay. And in order to get there, the main thing we will use is the complex plane. That will be our main tool. So we'll use that the low energies and high energies are related by analyticity. Okay, and through essentially dispersion relations that I can say the name because Sasha has been writing them since day one. So the sort of dispersion relation that Sasha has been writing, if you look them at face value, they really make the physics at some energy is given is related to some integral of all other energies. So this dispersion relation really make the UV and the IR talk to each other. So that's going to be our tool. Okay. So the goal of today is to convince you that there's physics in analyticity. Okay? It's not just a mathematical thing, there's this physics in it. So, and it's related, it's really a statement of causality. And we'll do a bunch of examples to do that. So the main question about the program. Great. Yeah, so what I'll be discussing is actually an expanded version of an appendix of the CMZ paper, Camano, Malacena, Lechang Malacena paper that I mentioned in the first lecture. And the setup is very simple thing. Imagine like undergraduate setup. You have a pulse that you send into some black box. It's copyrighted, trademark, don't know what there is in it. Magic black box. And out comes some other pulse. So there's a pulse, let's call it psi in. And the pulse will be a function of time. But you can also think of it as a function of x, because we're imagining a wave that's moving, t or x. And then there's something that comes out. And we'll assume that this box has some properties, which are going to be actually the properties that are relevant for a scattering amplitude viewed as a black box. So the first property is that it's linear. So psi out is a linear function of psi in. It's translation invariant. It's causal. And unitary. It's a very special box. Okay, so let me explain each of these things. So linear, okay, means the obvious thing. It means that psi out of t is some integral over dt prime of some kernel t prime of psi in of t prime. Okay, so the sum integral kernel that relates in to out. Okay. That it's translation invariant means that you can diagonalize this kernel by doing a Fourier transform. It's only a function of t minus t prime. So you can write in Fourier space psi out of omega is equal to some transfer function, which I will call S, times psi in of omega. Okay? So it's just basic statement about these properties. Now what does it mean for a box like this to be causal? So the way we understand it, I think it's the most reasonable way. And if you have a function of time, so the idea is the output should only depend on the past, not the future. So yeah.
You're saying this is invariant. Do you mean there are some octaves of this S omega?
No, it's just the fact that translation invariance means that this kernel is only a function of time difference. Therefore, when you Fourier transform this convolution, it becomes a product in Fourier space. Yeah. Yeah. I can put here, and that becomes k of t minus t prime, which becomes Fourier transform of S. So causal, the statement is that if you send in a pulse, which vanishes for t less than 0, then the output should also vanish for t less than 0. Okay? If psi in t equals 0 for t less than 0, that implies same for psi out. Okay? And because the box is time translation invariant, that's all I have to say. So not what?
It's a non-relativistic system.
No. No. So eventually we'll use it in a maybe I can sketch a scattering process. So if this is time, the way we'll actually use it in quantum field theory is that we'll imagine we have a wave here, and we're sending it through, and we're asking if this wave here got time advance or time delayed. So, but the important variable will be t, but t is really like retarded time. It's a proxy for x. X and t are a proxy for each other in this sort of wave scattering, because the wave is moving. Yeah.
The statement about the convolution you made about S of omega, does that assume some analyticity property of k?
Not yet. Yeah, exactly. Yeah. So I'm. Yeah, so the question is, am I assuming some kind of analyticity or regularity properties of K or something like this? So I'm trying to make the minimal assumption here. So this is a physics lecture, but the idea is that I'm assuming that K is a function such that its Fourier transform makes sense. Okay? And there could be various space of functions for which that's the case. And in fact, unitarity is going to pick us a particular space of square integral functions for us. But a priori here, I'm just talking about anything whose Fourier transform makes sense. Uh-huh. Yeah. Yeah, we'll come up in a second, yeah. Yeah, there will be, if K is a distribution, you might wonder to what extent, but this statement is well defined as the level of distribution. If you think of this psi out as a distribution, all of this makes sense. Because this statement makes sense for distribution. So all of this statement makes sense for the most violent type of functions you can imagine that ended Fourier transforms. Okay, I'm trying to be as general as possible. And unitarity will mean that the square norm of this does not increase.
So I think it's easy to see the causality by the statement goes down.
Yeah.
But is this statement strong enough to imply that causality back? Or is it like
In this model, it's a definition of causality. Yeah. In the QFT, this will somehow be related to vanishing of space-like commutator in terms of the retarded time. But in this model, it's just a definition. And unitarity is a statement that the square norm of the output does not exceed that of the input. And I'm allowing it to have some loss. Maybe the particle got lost, it got stuck or something. So that's going to mimic inelastic channels that Sasha was discussing yesterday. So the 2-2 amplitude, the probability of that if you do a 2-2 scatter, if you scatter 2 particles, the probability that 2 particles come out can be less than 1 because maybe 3 particles came out. Okay, so that's what this inequality represents physically. Okay, but on the other hand, the probability that 2 particles come out cannot be bigger than the probability of what you sent. Okay. So the claim is that, I think it's a physics level theorem, and I think with the appropriate definition about space of function, you can make it a map theorem, that there are 2 theorems you can show. So if you assume property 1 to 3, these properties, this causality property, claim that it implies that S is an analytic function in the upper half plane. Is analytic in upper half plane. And not just that, and not exponentially growing. And sub-exponential, I will define exactly what this means in a few minutes, and sub-exponentially growing. So causality is the name about analyticity and a little bit more than that. So sub-exponential is a bit weaker than polynomially bounded. But yeah, we'll see momentarily why that happened. And the theorem is that if you have properties 1 to 4, so if you have causality and unitarity, then you have all of the same property, but in addition is bounded and bounded, so S is less than 1, throughout the upper half plane. This last property is why I'm bothering to really explain this thing. So this first property may be familiar from a course you had in undergrad about signal analysis. But this property that the magnitude of S is bounded through the whole upper half plane, maybe a little bit less familiar, but it's actually very important for the story. Yeah?
The 1 through 3, is that sub-exponentially growing in the whole upper half plane?
Yes. Yeah. So maybe I can state exactly what this means. Sub-exponentially growing means that S is less than exp of minus epsilon imaginary part of omega times a constant for any epsilon. So for any epsilon, it decays faster than that exponential. Yeah. So that's a statement about when you go away from the real axis. Yeah, so I want, right, plus. Thank you. Thanks. Yeah, it's less than plus epsilon. Yeah, great. Yeah. Maybe let me erase it and say it better. Is that S times e to the minus epsilon imaginary part omega goes to 0 for any epsilon. Yeah.
So number 3 looks like retarded boundary conditions. Normally
Yes.
in QFT we're using Feynman boundary conditions.
Uh-huh.
How does that play in here?
Ah, excellent question. And I think I will have to leave this question to Sebastian, but I can give you a sketch, is that these properties, the thing that the single model will apply to most literally is not the usual time order amplitude, but it's going to be the expectation value of this is 1, 2. This is going to be the expectation value of a commutator in a scattering state. And this commutator turns out to be the same as the amplitude at positive energy and the complex conjugate amplitude at negative energy. So this commutator is actually related to amplitude, but is a more fundamental object. And because this commutator vanishes space-like, it satisfies this property of the single model. Yeah, it's an excellent question. Yeah. But yeah, the time order amplitude does not satisfy this property. Okay. So let's get some intuition and for why this is true. So here are 2 ways to think about property A. Sorry, did I call it A? Okay, let me call this statement A and the other statement B. Okay, so I will spend some time about A. So the simplest way to understand A is to look at the inverse transform. Sorry, the direct Fourier transform. So you can formally express this. So the statement that we're describing is that this kernel vanishes for t minus t prime negative. So they basically mean that S of omega is some integral that starts at 0. It definitely does not have support on negative time of dt, kt, exp of I omega t. And so we have to do an integral. So we're assuming that the Fourier transform of this kernel works and makes sense. And you see that if you put omega complex to be, say, a plus ib, I don't like blue chalk because I think it's hard to see, right? Take yellow. So this thing here is exp of I a t minus bt, and t is positive. So we see that intuitively, if the integral makes sense for on the real axis, turning on a positive imaginary part for omega only makes it more convergent. So if the integral makes sense for real, it must make sense for complex. Okay? If the integral makes any sense in the distribution or whatever, if integral makes sense for real t, real omega, B makes it better. So imaginary part makes it better. Yeah, B makes it better. Only in the upper half plane, exactly. Because if you go to the lower half plane, now instead of adding a convergence factor, you add a divergence factor, and now the integral may diverge. Yeah. A very simple argument, but I don't quite like this argument because it doesn't add you useful. It doesn't give you a lot of control over violations. And this also doesn't give you abstractly, if this case of distribution, the behavior at large frequency is controlled by how singular distribution it is. It's not a very. I think to me, I prefer to do a different argument using the inverse transform. Okay. But at least this should be this simple argument should give you intuition for why the thing is analytic in the upper half plane, right? But we haven't quite explained why it's not exponentially growing. So the inverse transform is, okay, we're going to characterize functions that vanishes at negative time. So let's write f of t as the integral of d omega over 2 pi x of minus I omega t times f of omega, okay? And let's take a concrete example. Suppose I have a function f of omega, which is I over omega plus I, okay? Okay, you can do this Fourier transform. All of you can do this Fourier transform analytically, but the game we're going to play is let's try to estimate this. Okay? Okay. The first thing you should probably do whenever you have an integral and you want to estimate it is to plot it. Re of f x to the minus I omega t. And if you plot it, it's going to look like some weird oscillatory thing. And then your job is to estimate the area under this curve. Can anyone do this by eye? Maybe some, yeah, there's going to be some cancellation. So the area is probably not bigger than the area of the first blob here. But apart from this estimate, I can't say anything, right? Your brain is not able to do that. So the method, so how to estimate, there's a method to estimate Fourier transform. In general, it applies to any oscillatory integral. And the systematic method is to use the complex plane. So what you're supposed to do is you notice that, for example, suppose that t is negative. And okay, we can do the other case after. Suppose t is negative. And this factor is x of plus I something omega. And therefore, you see that if you add a positive imaginary part to omega, you make the integrand smaller. Adding plus imaginary part omega makes it, I have to write bigger. Makes it smaller. Okay? And then here's the rule to do estimate. It's very simple, but it's a golden rule for oscillatory integrals. You estimate for how big the integral is it's how small you can make it by deforming the contour. Okay? There's a philosophy between steepest descent, but I'm not going to assume that there's a saddle point. I'm just going to try to make the integral as small as possible. That's going to be my estimate. Make integrand by deforming contour. If you remember one thing from this lecture, that would be that. So let's do this in example. Let me continuing this example here. So that's my example again. So if you do this for this function f of t that we just defined for this I over omega plus I, you see that for t less than 0, you can, in the omega plane, you have a pole at minus I, but there's nothing up, so you can keep deforming the contour up. And if you're at a plus ib, you have an exponential of minus t times b, so it gets smaller and smaller, so you just get 0. Okay? So that's how you can see that this particular integral is 0. On the other hand, at positive time, now you will naturally push the contour down to make it smaller, and then you will hit this pole, and then this pole, well, the height of this pole gives you an estimate of how big the integral is. And in fact, here you can calculate the residue of the pole, and it tells you exactly what the integral is. Okay, so it's going to be e to the minus t. Okay, so that's what this integral gives. Yeah?
Why do you call this an estimate? It seems like I'm completely
Yeah, but if you had a more complicated function than this one, it would just be an estimate. Because in general, if t is fixed, so we'll do other example later, but in general, if you have a complicated integral, well, here there could be singularities, but maybe there are some very complicated essential singularity that you're not able to compute the discontinuity across, then you'll still be able to at least say that the singularity controls how big your integral is. Okay? I agree. Often this is not just a method to do an estimate. Often this is actually a way to compute integral. But yeah.
So for example, what I'm supposed to do is I get from the contour, and then I estimate the value of this development.
Yeah. Yeah. So roughly the size of the discontinuity and the size of the position and the size of the discontinuity are what control the size of the integral. And the subleading one will be smaller if t is large enough. But if t is not very large, then maybe the smaller ones also contribute. The ones that are further below. And the important thing about this argument, the way it connects to theorem A, is that this argument will have worked. What we needed is the integral to decay when we have this factor x minus tb. So for the integral to decay to vanish for any negative t, we exactly need this statement that after multiplying by any exponential, it goes to 0. Okay? So the sub-exponential growth is exactly the statement that answers that your Fourier transform vanishes for negative time. Okay? So it's true for any sub exp s of omega. Okay? Yeah?
Why do we need the integral to be oscillatory here? What's special about this strict oscillatory integrals?
That's a good question. Yeah, the question is, suppose you have an integral that's not oscillatory, then I think the best way to estimate an integral that's not oscillatory is just plot it and estimate the area. So the reason you do this for oscillatory integral is that on the real axis there are cancellations. Yeah. Ideally, what you would want to do, if you really want to do something like WKB, you try to find a contour of constant phase along which there are no cancellation. But for a Fourier transform, that's not always possible. Okay, let me, just to exemplify this property again, let me give another example. So suppose you have a Gaussian, f of omega equal x power minus omega 2 over 2. So in this case, well, you all know that the Fourier transform of that is a Gaussian, and it's not a causal function. It has support on both t less than 0 and positive t. And that is tied to the fact that this Gaussian, if you evaluate it at a plus ib, is equal to x power minus omega 2 over 2 plus minus a squared over 2. So the magnitude of this is this plus b squared over 2. So you see that it grows in the complex plane. So the fact that the Gaussian grows in the complex imaginary direction is why it's not causal. Okay? So analyticity is really not all you need. So causality is not just analyticity. Okay, so analyticity in upper half plane is not enough. Okay, just want to make this clear. Causality is a statement about analyticity and a statement about the growth. Okay. So the other property about theorem B, so I will not actually give a proof of there. There's a nice proof in this CMZ paper that I quoted before, Appendix D. And I will not do the proof, but let me explain a bit how it works. So by definition, the statement of the unitarity that I postulated here, if you say that psi out of, by Planck-Cherel theorem, the integral over time is the same as the integral over frequency. So the statement that this is true for any function, since psi out is s times psi in, just unitarity by definition mean that s is less than 1 on the real axis. Okay? So a priori, you would have thought that your function is only bounded on the real axis, but it could, in principle, grow a little bit away into the complex plane. The thing that makes this true is the variant of the maximum principle in complex analysis that's true for the upper half, in the upper half plane. Actually, if you have this sub-exponential growth in the upper half plane, combined with analyticity and boundedness on the real axis, it actually implies that it's bounded. Complex analysis alone is strong enough to imply that it's bounded throughout the complex plane. So this plus this equal S omega less than 1 in upper half plane. Okay? So this may be something that you have not seen in undergraduate C analysis, but this is true fact about unitary boxes. Okay? Uh-huh.
Maybe a little bit irrelevant, but
Yeah.
like, there are similar theorems for like functions with say more than one more than one complex variable.
More than one complex variable. Yeah, that's a good point. For amplitude will be that would actually be tremendously useful. But for amplitudes, we actually only be looking at one slice of it that's parameterized by the overall energy in the rigid limit. So the way we'll use this statement is by projecting the amplitude into a one-dimensional complex subspace. But maybe a multidimensional version of a statement could actually be useful. I don't know. Yeah, I think the name that I'm supposed to pronounce it is Fragment-Lindelof. But there actually is a very concrete proof that does not rely on that given in this appendix also. It's very nice, Appendix D there, the CMZ paper. Yeah?
So that's the zero kernel that's set for property.
Yes.
But I mean, unitarity, I would assume that you can just go back in time.
Okay, yeah, that's a good point. Thanks for the question here. So so the question is, if the system is unitary, why cannot reverse it? So that's a good question. So in terms of in the context of amplitude here, when we say that the S matrix is analytic, is unitary, that means that the S matrix has a whole collection of items, 2 to 2, 2 to 3, 2 to 4. It's a big matrix with all these options. And that, if you have this full unitary evolution, you can invert it and go backward in time.